主要呢，我们就是做的是如何把 deep learning 在edge device mobile，就是说手机这样上面平台上面能够最优的实现。我们说的我们这边用了一个最优这个词，但是我们到后来我会讲一下我们为什么觉得我们这个接近吧，这就是接近最优的implementation 吧。然后 deep learning 呢是 everywhere， 就是呢有很多的 application， 但是其实呢还是不够everywhere enough。就是因为呢，大家还是觉得这个 deep learning，我们真正需要放在所有的 device 上面，让大家都更加到处都是能跑 AI 的这些项目。但是现在呢，目前还很难做到这一点。这 deep learning 呢，大家都认为它的 inference phase 是需要放到 low power embedded system。
言辞要不用英文讲好了？
有问题吗？需要用英文讲吗？
我说之前像他说用英文讲可能好一点嘛。
Okay. So the deep learning has a large model size. So there is some challenge for this. It is projected that most of the deep learning systems, at least the inference phase, will be deployed in the low power embedded systems. For example, like the autonomous driving systems, like the UAVs, underwater submarines, etc. So there is a challenge here. So this kind of systems have multiple sensor inputs. It has 3D sensors from the radar and has the 2D sensors from the imaging videos. It may have the audio sensors. And this kind of sensors makes a multimodal deep neural networks. So overall, it becomes a much more complex deep neural network than just ImageNet. Really, ImageNet is just a toy benchmark compared with this kind of actual realistic applications. However, there is a limited power budget and a very limited form factor constraint. And we need to achieve the real-time performance requirement. So we need to react in the order of 30 milliseconds, 40 milliseconds. Otherwise, it may be slower compared with a human's reaction, and it may cause some damage. There may be some safety concerns. So this is a reason that people are working on the deep learning hardware from the CPUs, GPUs, FPGAs, and also the dedicated AI chips. Actually, we have worked on AI chips before, but at this moment, we're not going to talk about AI chips. We are going to mainly focusing on the software solution of compression and compilation-based acceleration. And we're going to focusing on the general purpose device to see that how that works and behaves actually better compared with dedicated hardware. So here is a gallery of our actual chip tapeouts that we have participated at, or we have worked mainly on our own. So this is mainly the new computing paradigms, like the stochastic computing-based neural networks, neuromorphic encoder decoders, processing memory PIM, deep neural network acceleration, and something like the analog DNN accelerations. So these are something like the emerging technology base. So they are mainly proof of concept, very difficult to actually implement a full neural network. So here is standard CMOS-based digital logics. The top, some are got accepted in ISSCC or JSSC, the with pruning and with quantization using the block circulant matrix. And then at the bottom one, including the pattern pruned ASICs, and also the structured pruned ASICs, which is in collaboration with other research groups and also the companies. Here is a continuation of the superconducting circuits that we jointly designed with Yokohama National University. So this is the superconducting devices which they have built it and then they tested on it. And we have built the so-called world's first deep neural network accelerator using the superconducting Josephson junctions. And actually the technology can even afford a fast Fourier transform processor with 8 inputs. So overall, it can achieve, so theoretically, the good thing of the superconducting is almost achieves 0 power energy consumption. But in fact, because of the cooling power, so this kind of claims is difficult to hold in the actual systems. So here we show our current mission. Previously, we were mainly discussing things, showing some results on the hardware. But later we're going to mainly focusing on the software solution for the off-the-shelf mobile devices, because anyway, they are utilized in most of the places. And our goal is to achieve the real-time performance of all deep neural networks. We're going to say all deep neural networks, maybe except for a few cases, like the recently invented GPT-3. Maybe we cannot achieve real-time for this kind of applications, but for most of, or almost all, maybe we can make it real-time. So this is achieved using our current technology, so-called compression-compilation co-design. So we're building the compilers, we are using the compression techniques, we're going to make them match each other. And in together, they are going to achieve acceleration that cannot be achieved before. And our framework can enable the real-time AI on mobile devices. So first, we're going to have a survey of the deep model compression techniques of the neural networks. So the first technique is weight pruning. And one of the representative one is a non-structured pruning that can prune the arbitrary weights. So the remaining structure is a sparse structure. But this technique has been proposed for less than 5 years. But whether it has been widely adopted, the answer is no. There is very limited actual deployment. The reason is because 2 reasons. One is a small thing, is that the original work has very limited weight pruning factor on the convolutional layers. For example, less than 3 times for AlexNet. But this is a minor thing, because we have algorithm. We can increase this rate. We can increase this to 10 times, 20 times, or even 100 times. But is this good enough? The answer is also no. Because after pruning, it becomes a sparse structure, and the index are required for the sparse format. So this will cause speed degradation mostly in the CPUs or GPUs when the hardware parallelism needs to be maximized. So this is a reason that people are more focusing on the so-called structured weight pruning. So structured weight pruning, including filter pruning and channel pruning. For a neural network layer, for a convolutional layer as an example, it can have a weight tensor format, as we can see from the left, or it can have a weight matrix format, as we can see from the right. So weight tensor format can be transformed to weight matrix format is called the general matrix multiplications. The previous non-structured pruning can prune arbitrary weight. But in structured pruning, the filter pruning prunes the entire filters, and channel pruning prunes entire channels. So we can see when it's going to be transformed into a matrix, then the remaining computation is actually still a full matrix, but the size is smaller. So the parallelism can still be maintained. So overall, this kind of technique is hardware friendly, but results in accuracy loss due to the coarse granularity. So we want to mitigate this kind of shortcoming. And later we are going to see how are we going to achieve accuracy and hardware parallelism together. So there are also other techniques like the weight quantization, including the binarized weight, ternary weights, 2-power weights, fixed length weights, etc. They are somewhat hardware friendly, and multiplication may be eliminated in binary, ternary, or 2-power weights. But the thing here is that for mobile CPUs or GPUs, it's very difficult to support a very deep binarization or ternarization. So mobile CPU mostly supports 8 bits fixed point, and mobile GPU cannot even support fixed point. So they can at most support 16-bit floating point. So this is the reason that weight quantization is not our focus, because we want to achieve the maximum. We are focusing on the off-the-shelf mobile devices. And then there are some weight clustering techniques, but this kind of techniques, almost no one is using it at this moment. And there are some also other techniques, like our previous invention of the block circulant matrix-based neural networks that we are going to divide a whole matrix into different blocks and using a circulant reformulation of each block. This can reduce the storage and computation, as the computation is done using fast Fourier transform. For this work, we're going to focusing on the general stuff. Like we're going to find a uniform solution of this kind of weight quantization, pruning, and also the block circulant stuff. We see that they look very different, but actually they are the same problem. At least they can be solved using the same technology framework. This is ADMM, or alternating direction methods of multipliers. With weight pruning and quantization, they are just special cases of the general clustering problem, and therefore it is compatible with ADMM. We see the weight pruning is essentially clustering because it's just cluster a number of weights to 0. We see weight quantization is essential clustering because it's going to cluster the weights into the predefined quantization levels. Even the block circulant matrix is clustering because we're going to divide into different blocks. As we can see, the red weights are in one cluster, the green one are in one cluster, the purple one are in one cluster, so on and so forth. So all of them are essentially a clustering. In fact, we can prove that without this kind of clustering, we cannot reduce the weight storage. So this is a reason that it can be solved using this ADMM framework, which is an effective mathematical optimization framework that we decompose an original problems into 2 subproblems. And they're going to be solved iteratively until convergence. Consider this optimization problem, minimize f of x plus g of x. In ADMM, the first step is going to rewrite it into minimize f of x plus g of z, subject to the constraint x equals z. This looks a little bit weird because if x equals z, why do we need to write separately into x and z? We can write into just x. The reason is because ADMM is going to decompose this original problem into 2 subproblems. One on x, another one on z, and they are going to be solved iteratively until convergence. The first subproblem is minimize f of x plus a quadratic term q1x given z. Here we are given z and we find x. This q1 is a quadratic function. In the actual problems of joint weight pruning and quantization, we consider the most complete problem that these two are done simultaneously. The first subproblem is minimizing this loss function. And this loss function is a function of the weights. We want to find the weights, plus 2 regularization terms. The first one is a quadratic term for pruning. The second one is a quadratic term for quantization. So here, both terms are quadratic, so they have the same complexity and solution methods in SGD, stochastic gradient descent, as the original deep neural network training. So this subproblem can be solved. The second subproblem is minimize g of x plus a quadratic term q2x and z given x. Here we are given x, and we want to find z. In weight quantization and pruning, and quantization, actually for the weight pruning, the second subproblem is given here. We are given w and we find z. And for weight quantization, it is shown here, we are given w and we find y. So actually there is an optimal solution for these clustering problems. For these 2 problems, the optimal solution is Euclidean mapping. And this optimal solution has polynomial time, which is straightforward solutions that we omit because of them. But we can check the papers and then further details. Okay, so with the second subproblem, we get the z values. From the third subproblems, we have derived the y values. And then we get back to the first subproblems. We got z, we got y. And we're going to solve this first subproblem again in an iterative manner. So essentially, this kind of ADMM is a dynamic regularization procedure. From this kind of procedures, we are going to solve these W's, satisfying this kind of constraints, and eventually it will converge to a weight pruning and quantization solution. But the issue here is that this is just a dynamic regularizations. Previously, people are also using regularizations, like IO1, IO2 group class of this kind of regularization. For example, we can minimize the loss function plus a regularization term here on the weights. This is IO1 or IO2, whatever the definition is. So what is the advantage of the ADMM, the dynamic one versus this static one? Just because yours is dynamic? This is not a very valid reason. The major reason is like this. We are using the fixed regularizations. We are penalizing all the weights. And the weights are penalized even after the convergence. We want to compress the value of all the W's. But this is not the goal of pruning. Pruning is not to make all the weights zero. Pruning is going to make a target number of weights zero. If you want to prune by 10 times, you make 90% of the weights zero. The remaining 10% of the weights they want to increase in their magnitude. Otherwise, how can they compensate for the effect that the rest of 90% of the weights are already pruned to zero? But this kind of fixed regularization is going to penalize all of them eventually. So this is not the correct goal, and then it causes accuracy degradation. On the other hand, if we consider the ADMM-based solution, that's this kind of dynamic updating, when the 90% of the weights are already zero, and the remaining weights will not be penalized. So this is a reason that we got this kind of results. So this kind of work originates from AlexNet. So we go to AlexNet again. So y-axis is a top 5 accuracy. At this moment, it's not fair to use 80% again. We can achieve easily 83%, 84% thanks to batch normalization and PyTorch. The x-axis is the overall pruning rate. We can see compared with the prior work, we got far higher pruning rate. Here, this is an almost 100 times weight reduction, means that there is only 1% of the weight remaining, and the accuracy is still okay. And with 64 times weight reduction, we got similar accuracy as the prior work starting accuracy. So this is a difference here. For this kind of gap, and we can see the effectiveness of our work, although it's a non-structured weight pruning. So this is a standard benchmark for testing, like ADMM-NN, CIFAR, SVHN, ImageNet, and also TIMID for speech recognition. And later we're going to see much more data sets. So first, we see the most simple data sets. ADMM-NN is not a very good indicator, to be honest, because it's too simple. It's very difficult to make the accuracy lower than 99%. In fact, we can prune by 700 times the number of weights, and the accuracy is still 99%. There are only 600 weights parameters remaining. This is even fewer than the input pixels, which is 28 by 28, 784. So actually, we can get our model, the number of weights, smaller than linear regression, because linear regression even requires 1 weight per input, but our accuracy is still 99%. We showed the results on AlexNet, and we see more results on VGG and ResNet 50. And we see the ResNet 50, we can get 9 times with pruning without accuracy loss, which is shown here, and 17 to 20 times with less than 1% accuracy loss. So that is non-structural pruning, and we see the results on the joint with pruning and quantization, because we believe that pruning needs to be combined anyway with quantization. So these are still working on the LearnNet, AlexNet, and ResNet, and the later two are on the ImageNet. We see this LearnNet again, and this is the maximum compression that we show in these slides. we can achieve 700 times reduction of weights. And simultaneously, we can achieve 3 bits with quantization, and the accuracy is still 99%. So the overall data compress rate is 6,645 times, as we can see here. And for the other one, like LXNet or ResNet 50, we can compress by 100 to 300 times. But this is our results 1 year ago. At this moment, we are clearly not satisfied with this kind of results. Then we ask this question, what's wrong here? What is missing here? Remember, our goal is to achieve the real-time execution of all deep neural networks, all AI applications, using a mobile device. Then can we use this kind of optimization for mobile devices? Very difficult, because this relies on non-structured pruning, which is very difficult for parallelization, and quantization, which is difficult to implement on mobiles. So the answer here is no. If we take this YOLO V4 on the MS CoCo dataset as an example for object detection, if we use a current acceleration framework like TensorFlow Lite, it requires 700 millisecond inference time. This is clearly far from real time. And how to make it real time? We can test non-structured pruning and structured pruning. Remember this, again, non-structured pruning prunes arbitrary location, and structured pruning prunes the whole filters and channels. If we work on the non-structured pruning, we got 8 times compression with less than 2% MAP loss. This is good results, but this is not supported in the prior acceleration framework. If we want to support it, we have our compiler and we can support it ourselves, generating codes. And we got only 1.4 times acceleration using our compiler. This is not good. If we use filter and channel pruning, is that good enough? No. We got 19% MAP loss with the same amount of compression. Although the compression can be directly translated into acceleration, but we don't want almost 20% loss in accuracy. This is clearly not acceptable. So this is the reason that we found that there is a missing angle here. Previously, people believed non-structured pruning is accurate, but not hardware friendly. Structured pruning is hardware friendly, but loses accuracy. This is also shown in our previous results, using this YOLO V4 as an example. But can we achieve both? Can we achieve simultaneously accuracy and hardware performance? Let's see what we have missed. What have we done so far? If we want to do pruning, we need to first determine a specific degree of regularity. Like structured if we prune the whole filters, or non-structured if we prune the locations. Is there something in between? There's something in the pruning scheme. After we have determined the pruning scheme, and then we can perform the compression and train the weights. This is the pruning algorithm. Previously, we have discussed everything about ADMM. What is ADMM? ADMM is essentially a pruning algorithm. We have solved this. We have some improvements on this, like reweighted regularization, but this is somewhat like incremental optimizations. What is missing here is the pruning scheme. Is there a better or optimal pruning scheme that can be both accurate and efficient? There is something that is our key contribution of the fine-grained structured pruning that achieves this goal. We're going to discuss about 2 schemes of the so-called fine-grained structured pruning. The first one is the pattern-based pruning. So this is an overview of the pattern-based pruning. We can see that this is actually a convolutional filters and is using 3x3 kernels. And for each kernels, we are going to either assign a pattern or completely pruned. We can see this one is assigned a pattern with a square shape. This one is also with a square shape, and this one is also shown as a different patterns. And if the kernel is completely gray, it means that it is completely pruned here. So the pattern means that only the weights, the colorful entries have values, and the rest of the small entries, they are pruned. So they need to follow this kind of patterns and the specific value distributions. During the pruning, we are going to select the patterns from a predefined pattern library. And here is a pattern library. We can see it has a set of patterns to select from, like this one, this one, this one, this one. And this kind of pattern libraries are going to be automatically generated. You can refer to our paper recently in the training phase. So during the training and the compression, we're going to select a pattern for each kernel. We're going to train the weights on the pattern. For example, these red weights, they need to be trained. And we need to prune the rest of the weights. Those green weights need to be eliminated. And this is achieved using our enhanced ADMM-based pruning algorithm. So this is our first type of fine-grained structure pruning. What is the advantage here? We want to say that it is simultaneously accurate and efficient. Why high accuracy? At the theory level, this kind of pattern-based pruning, people want to say that the kernels should be a pattern. Kernels should not be a square size because this eliminates overfitting and it has a higher capability of feature extraction. Actually, we have used some standard testing of without pattern pruning the original network and with pattern pruning using 3 metrics. And consistently, it all shows that the pattern-based pruning got better feature extraction results, as we can see on these figures. And at algorithm level, with our enhanced ADMM, because of overfitting eliminations, it got higher accuracy consistently. Like the top 5 from ResNet 50 is from less than 93% is increased to 93.3%. We simultaneously reduce the number of weights and increase the accuracy. The second question is that why it is fast? We know that it reduces weight and may increase the accuracy or maintain the accuracy. But it still looks like irregular because we may assign different patterns for different kernels. Why it is fast? Because the compilers will play the key role here. Suppose that there are different types of filters, different types of patterns, 2 patterns here. And then the compiler can perform the code generation with a filter and channel reordering. And after the reordering, it's going to group the same patterns together. And when they are grouped together, we are going to assign different patterns to different threads and different patterns to different cores. For each core, it can work on simultaneously 1 type of patterns. In this way, it can maintain the instruction and thread level parallelism, the maximum parallelism, on a mobile CPU or GPU. And finally, at hardware level, 4-entry patterns is actually match the SIMD structure of the mobile CPU and GPU because 1 core can work on 4 instructions or 4 data simultaneously. So 1 kernel can be done using 1 clock cycle, and this cannot even be achieved if we are using the previous 3x3 or 5x5 kernels. So this is a reason of the pattern-based pruning. The second type is block-based pruning. For 3x3 and 5x5 kernels, block-based pruning will not perform as well as pattern-based pruning. But later we're going to see why we need to use block-based pruning as well. Our convolution layers can be represented in the weight tensor format or weight matrix format. In the weight tensor format, it's going to divide each weight tensors, this whole weight tensors, into different blocks. As we can see, this is one block, this is one block, this is one block. Another number of blocks has M filters and N channels. Here is divided here. So for each block, we are going to use the same pruning format. Like we can see for this kernel is using this shape. All of these kernels in this block having this shape. I mean, the gray ones, the gray entries are the pruned ones. So this is a weight tensor formats. In weight matrix formats, for this weight matrix, we're going to divide into different blocks. And for each blocks, we're going to apply independent row and column pruning here. So those kind of rows and columns are already pruned, and then the remaining weights, they form a small weight matrix. So independent row and column pruning. We prove that these two are equivalent. For the convolutional layers, they are equivalent. For fully connected layers, they only have the weight matrix format. And ADMM-based weight pruning can be enhanced for the automatic pruning into this kind of shape with the help of the group plasma. So this is the overview. So what is the advantage here? This kind of pruning may not work as well as pattern-based pruning because it has lower flexibility. But it is applicable to convolutional layers of different sizes, not only 3x3, 5x5, but also 1x1 or even larger one like 7x7 or even 11x11. It applies for fully connected layers, including the recurrent neural networks, transformers, etc. So it is widely used in almost all neural networks. It can be even generalized to the 3D convolutions. As we can see from this example, from the 3D kernels, we can also generalize this concept. But the idea, but the details, we're going to omit it here. So what is the advantage here? Why it is more accurate and also can achieve a good speed up? So it can achieve a relatively good accuracy because it has the flexibility in the independent pruning of each block. Different blocks can be pruned differently. This is different, more flexible compared with the whole matrix pruning. And it can be fully autonomous in the ADMM-based algorithm. Meanwhile, it can achieve a high hardware performance with the help of compiler. Why? Why this kind of thing can still not sacrifice the hardware performance? The reason is because a weight matrix in computation is generally very large. It cannot be finished in mobile devices or even large-scale GPUs in one clock cycle. It needs multiple clock cycles. So because of this, even if we are going to divide into different blocks, the remaining computation can still be parallelized, achieve the maximum parallelism on device with the help of compilers. And this kind of overhead in eliminating the whole rows and whole columns can be minimized by compiler code generation together with storage. So the parallelism is achieved here with the compiler as the key bridge between the algorithm and hardware. The key reason is because the available parallelism on the weight matrix is much larger compared with the actual parallelism degree on a hardware device. No matter this hardware device is mobile CPU, GPU, FPGA, or even a large scale GPU. So the compiler code generation is the key to victory here. As we can see from the pattern-based, the compiler is using a purely software level solution, grouping the same patterns, assigning different threads, and assign the threads to different cores for parallelism. For the block-based pruning, is using a software hardware co-design solution because the remaining computation in each block is still can be parallelizable on the mobile CPU and GPUs. The parallelism degree is still higher. So we call this framework CoCoPIE, which is Compression-Compilation co-design. So we show that compilation is a must. Accuracy and hardware performance. We want both, and now we can get both. We see this example. This is the accuracy versus inference latency of ResNet 50 on the ImageNet dataset, measured on a smartphone, Samsung S10, and using our compiler. We are testing on different block sizes with 6 times pruning for all layers. We can see the x-axis is a block size. 1 by 1 means that it is non-structured pruning. Arbitrary location can be pruned. The whole matrix block means that it is filter and channel pruning. We need to eliminate whole rows and whole columns. We can see with the increase of the block size, the blue curve is the latency. The latency rapidly decrease and then saturate. And this red one is actually the accuracy. The accuracy will first saturate and then rapidly decrease. Non-structured pruning has a good accuracy, and structured pruning has a good latency. But we see that there is a range of the block size. This range of block size can achieve simultaneous accuracy, high accuracy, as non-structured pruning. And because it can be parallelized on device, it can simultaneously achieve low latency close to the structured pruning. So this is a reason for us to get both. And this is beyond a mere trade-off. This is, we get the advantage of both accuracy and performance while hiding the disadvantage beyond the trade-off. So in our compiler-assisted acceleration framework, we are using a very standard and comprehensive compilation designs. So here, from the training, we got a sparse neural network. Of course, we're the first to support the sparsity in the compiler designs. We got a graph-based, layer-wise representation of the compressed model here. And from this compressed model here, we are going to go to the next step, which is the sparse model auto-tuning reordering, which is a core compilation technique. And what we generalized are the executable codes. C++ codes for the mobile CPU, OpenCL or OpenGL for the mobile GPU, together with a model storage. And our things, executions, can be directly deployed, both for CNNs, RNNs, transformers, and all other things, directly on the mobile device. So beyond that, recently we have developed an overall automatic design flow of the compression compilation code design. We can see this flow is shown here. From an AI application, we can do a pre-trained. We can search for the optimal models doing NAS. And then we are going automatic pruning scheme selection. This automatic selection needs to select the per layer pruning scheme, like pattern-based pruning, block-based pruning, or even other types of prunings. And then we're going to determine the compression rate per layer. And then we got an optimized model, go through the compiler code generation, and finally deploy on a mobile CPU or GPU. We want to show here that this is actually a training-free process. the automatic selection, and the automatic compression rate determination that do not require extra training. So this is significantly faster. Okay, so we're going to show our results. What can we achieve using a smartphone? This is the execution time comparison with a TensorFlow Lite TVM and Alibaba MNN on a smartphone. So we can see our CoCoPIE results are consistently the fastest and is much faster compared with the prior work. What we can achieve on VGG16 is 17.2 millisecond inference time just using a phone. This is over 50 times speed up compared with TensorFlow Lite, and more than 10 times speed up compared with Alibaba MNN and TVM under the same accuracy. We got 16 millisecond inference time for ResNet 50, and even less than 4 millisecond inference time in MobileNet V2. So nowadays, this is clearly the record of the MobileNet V2 under the same accuracy, less than 4 millisecond inference on a mobile device. And recently we got new results. We got 45 millisecond inference time on BERT with less than 1% accuracy loss. So BERT is nothing. It's really very simple stuff for the mobile phone. On the prior version of GPT-3, GPT-2, we got 150 millisecond inference. It can be implemented in close to real time on a smartphone as well. And we can potentially execute all deep neural networks in real time in a smartphone. And we're going to see where is this kind of gain comes from. How much gain is from the compiler and how much gain is from compression. We're going to make a summary here. So here are the results on VGG, ResNet, YOLO V4, and C3D. Actually, this is for activity detection. So we show the YOLO results on CoCo dataset as an example here. The first comparison is a compiler. We all work on the original model without any compressions. Same model. We see our compiler with MNN and TVM without pruning, and we see that our compilation is essentially 20% faster at least. The TensorFlow Lite is too slow. It is more than 700 milliseconds, so we don't even include in this slides because it affects the overall readiness of this slide. So this is advantage of our compiler. And next, we're going to see the advantage of compression. So in this comparison, we're going to see our fine-grained structured pruning scheme, which is our proposed shown here, versus our original model shown here. Under the similar accuracy, we can increase the speed by 4 or 5 times. So this is advantage of the compression compilation code design while maintaining accuracy. The third one, we want to compare with filter and channel pruning, the previous non-structured pruning technique. And in this comparison, we are going to compare our technique with the previous filter channel. Sorry, can you hear me? Can you hear me?
Yes.
Okay, with the previous filter channel pruning, and then both of them are working on ADMM-based solution. We are the same solution. And we can see we can simultaneously be faster. And we got higher accuracy because the filter channel pruning will got a significant accuracy loss if it's beyond 5-6 times overall compression. So we see the results, and the other results are also similar to this. And for this, we want to further compare with smaller models. Training a smaller models is a currently main focus. We want to train the tiny model, but it's very difficult to maintain the accuracy. we can see the YOLO V4 accuracy is shown here. If you want to train a small model like SSD or tiny or mobile net SSD or whatever the techniques, is got significant loss in the MAP. But our technique, it can achieve a much smoother loss in accuracy. And we can simultaneously get a significantly higher accuracy and also run faster using the same framework. These are our results, and those are the previous work on smaller models. We are all running in our compiler because our compiler is the fastest, and many of the previous compilers cannot support those kind of techniques as well. So when we break down the actual improvements, we see that first, our compiler is fast. It has 50% to 3 times speed up compared with the previous compilers. But compression also plays an important role here. Compiler, the pruning scheme and algorithm together, it got 2 times to 10 times potential speed up. We see potential speed up here because it's very difficult for them to work alone without the help of compiler. Without the compiler supports, they cannot be used. So this is a reason that there are not too many people working on pruning at this moment because it's very difficult. Currently, there is no compiler supports. If you train a smaller model using network search, there will be accuracy loss. This is already determined. But when the compression and compilation are co-designed, they are integrated together, things becomes different. Compiler can provide supports for compression, and compression can be compilation aware. And together we got 3 times to 20 times actual speed up. And here we show even more results when comparing with the dedicated accelerators. We compare with the Google TPUs, we compare with Aries, we compare with NVIDIA accelerators, we compare with IPJ solutions. We also can compare with others like Cambric and other things. And we can see that our energy efficiency and sometimes latency are mostly, if energy efficiency is almost always better, and the latency for some cases is also better compared with, of course, this is a cloud TPU and this is the edge TPU. This kind of dedicated accelerators. But we are just using a phone. Why? Why we can achieve this kind of results? We see these results on our results using on the ImageNet dataset versus all the prior dedicated IPJ solutions we have found so far. All of these solutions we can see shown here, where the x-axis is the top one accuracy, and the y-axis is the energy efficiency. And we can simultaneously be faster and also more accurate, more energy efficient and more accurate. Our results are clustered into 2 categories. One is the large-scale models like VGG or ResNet 50. One is a smaller set models like MobileNet V2. But they are showing superior results compared with the prior, even they are working on IPGA. Why is that? We want to find a solution, so we compare with this solution of ESE, which is an IPJ best paper 3 years ago. We want to review the reason. Is it because of the compression? Is it because of compilation? Or because somewhere else? We show that here, we see there is no prune. No prune, and we do not use quantization. And the energy efficiency is already 88% of ESE when they use 9 times pruning. We don't use pruning, they use pruning. And our energy efficiency is 88%. This is not the advantage of pattern-based pruning, structure-based, block-based pruning. We are always talking about pruning schemes, but this is without pruning when we just run the original neural network, we show this kind of results. What does this mean? It means that mobile phones are really highly energy efficient. No problem here, we got almost 90% energy efficiency as FPGA. So the reason, first, mobile phone is energy efficient. It is made from ARM or Qualcomm. They are the best chip vendors to making energy efficient chips. They can use the most advanced technology. Actually, they are the driving force of the technology. They make the most chips. Today, or yesterday, Apple have announced a 5 nanometer technology, but what can those kind of FPGA or dedicated ASIC use? 14 nanometer, 28 nanometer? I mean, the smartphone itself is essentially energy efficient. Our compression-compilation design is going to review the ability, release ability of smartphones. Previously, there is no compilation support. We can support, and we found that it's worth this work. So we see some results on the real-time AI on the mobile devices. Those are the results that we got 6 months ago. Those are very simple results at that time. So here is a result on automatic style transfer we got from the output inputs, and then we can automatically transfer in different styles. So you can see we can use different styles. And this is resolution upscaling. We got an input of low resolution, but in fact there is no low resolution in actual input. So from the camera, actually we are using a low resolution, and we output high resolution outputs. And here we see the automatic coloring. The input is a black and white videos, and automatically is transformed into colorful videos. Those are very simple results. And then currently we have much more better results, as we can see here. This is our results on YOLO-V4 object detection. We can see this can almost achieve something like autonomous driving. It got is our results on YOLO-V4. That is, this is even higher accuracy compared with YOLO-V3, and we can achieve on a smartphone. And then this is a real time for YOLO-V4 on the other data sets as well. And here is a 3D activation detection. We can do the activation detection. We can get 9 milliseconds per frame using our frame. And then it is clearly super real time, and it outperforming the prior work by 30 times speed up. And then here is a background segmentation, as we can see from the input, and then our smartphone is generating a segmented outputs. And we can see that we can also do something like the medical applications, like we got using a phone to detect immediately whether there is a COVID or pneumonia, or it is a healthy lungs. So this is also another applications. Yeah, so those are more difficult applications compared with the transfer or upscaling or coloring, which is really simple ones. And then most recently, we got 2 most complicated one that works on a mobile phone. The first one is open pose. We can see this kind of pose estimation that works for 20 frames per second, even on a large scale GPU, and we can make it almost real time. There's a little bit not real time at this moment, but almost real time just using a phone. Another one is a real time BERT. As we can see, this is a question answering. And then the BERT can immediately find the solutions just using this phone. So as we said, BERT is nothing for a smartphone, 45 milliseconds. So thanks to the contributors, as we can see from a CoCoPIE framework. And also this is also another smartphone real-time, that is animation. That is also real-time on a smartphone. So this is our media coverage, selected ones, and then this is our acknowledgement of the findings. So thank you very much. So welcome to our YouTube and BZhan channels. Just search, and then we are going to uploading more and more videos. So thank you very much. Thank you.